Okay, let me go ahead and share the screen.
Thank you.
Okay, can you see it?
Yes.
Okay, cool. Thanks, Ali, for the very canned introduction, and I'm very happy to be here to share my recent works. And thanks everyone for joining my talk. So this talk will be focused on a decentralized framework for ensuring power system stability in the era of heterogeneous IBRs and synchronous machines. So this is an unusually long title for my talks in general, but really I want to stress that in the future, the power system will be facing heterogeneous IBR resources, and it needs to be able to operate with each other with the legacy synchronous machines as well as the rest of the work, the network. So I think I can basically skip this part because Ali did a terrific job in introducing my background. I'll only perhaps mention that my research aims at addressing these problems of shifting to future renewable energy systems, and I integrate methodologies from analysis, control, and optimization to study the power system stability problem, control and system problems, nonlinear and dynamic, hybrid dynamic system problems, as well as the application in transportation and multi-energy systems. So at Hopkins, we have a great team that is integrated at ROSI, Ralph O'Connor Sustainable Energy Institute. We have a relatively diverse expertise spanning from fast time scale dynamics and control myself, as well as this control theory, Enrique, the wind energy system, Denise, as well as the market and policy led by Ben and Yuri. Last year, our team was awarded a highly competitive NSF grant and lead this 18 million research effort on carbon-free energy systems, and we're collaborating with industry and academics from the US, the UK, and Australia, which is a quite exciting initiative. Okay, so let's get started on the technical stuff. Today, I will talk about various research questions my group are working on regarding the dynamics, the control and stability of inverter-based power systems. I will actually split the time between discussing challenges in future low inertia power systems and a framework for decentralized stability criteria for inverter-based power systems. Some of the results are fresh out of the kitchen, so I very welcome any feedbacks or questions. Okay, without further ado, let's delve into the challenges in future low inertia power systems spanning from new dynamics, variable generation, and heterogeneous devices. The foundation of power grids are changing rapidly in recent years. We see a fast adoption of renewable resources, batteries, EVs, and high voltage DC lines into the grid, and the gradual retirement of synchronous machines. Conventionally, these large generators are all synchronous machines, and they have a large rotating mass that rotates at synchronous speed. For example, the pumped hydro, the nuclear plants, and they provide the base load in the system, and they will likely stay in the grid in the future. More and more inverter-based resources has been integrated to the grid in place of the coal-fired power plants. For example, in the world of wind turbines, there are two prevailing models, the Type 3 and Type 4 wind turbines. Wind turbine may use synchronous machine or induction generators. Although it has this rotating part, there is the power electronics interfaces that more or less separates the machine physics from the grid. Thereby the name inverter-based resources. As seen from the grid, the dynamics is dominated by the control logics enforced on the power electronics and not necessarily the physics of the machines. So this typifies the large difference between a traditional power system where you're dealing with synchronous machines with well-known physics to the new world of inverter-based resources, predominantly renewables. So for a system, if you're a system operator, you don't really see the physics of the wind turbine machines, Instead, you see the behavior of the control loops that the manufacturer has built into their device, which is proprietary information, and there are numerous possible implementations. So in summary, conventional generation featured by synchronous machines are centralized, large-scale, dispatchable, and dominated by physical laws, which are well understood. It has relatively slow dynamics and good interoperabilities. On the contrary, those emerging inverter-based resources are often decentralized, of smaller scale with intermittent or limited generation, and most importantly, their dynamics are poorly understood at the moment. Their dynamics are dominated by this controller instead of physics, and thereby they are heterogeneous. The traditional analysis methods focus on a set of pre-examined events and numerous and operating points. So rely on the fact that we can predict the load to a relatively well extent, and we have a good amount of dispatchable generations. We can afford to do linearizations, and the system is homogeneous. But in the future, it might be dangerous to assume the same things because the system will demonstrate high variability, nonlinear and hybrid dynamics, and a mix of heterogeneous components. I think there are a few key characteristics of few low inertia power systems. The first thing being the new dynamics. What do I mean by new dynamics? We can abstract the IBR model into these three main blocks that are system level control, the device level control, and the power electronics per se. The system level and device level control are perhaps the most relevant from grid perspective. These IBRs introduce new dynamics to the grid compared to conventional swing equations. This figure on the right provides the stability framework for power systems across time scales and the dominant states, including voltage, angle, and frequency. We can observe the conventional timescale separations among the dynamics of these dominant states. But in the new paradigm of IBR-dominated power systems, we can see the overall response speed is shifted to the faster spectrum, and there are also now more prominent overlaps across the timescales. So the naive integration of IBRs will cause instability problem, which motivates our effort in establishing a stability guarantee. Secondly, we also need to pay attention that with renewable generation such as solar and wind, there is often a limited and non-dispatchable energy source. This may cause problems for power system operation because the fundamental operating principle of power system is to ensure the power balance at every time instant. This also calls for the need of designing appropriate market or regulation schemes to ensure provision of grid services. The inertial response provided by rotating mass of synchronous machine was taken for granted, but this is not the case for IBRs in the future. Third, because of the dynamics of IBRs are governed by the enforced control laws, there is much more flexibility, and in future systems, we need to make sure all these devices properly interact with each other with synchronous machines and with and through the network. Not that the faster loops in inverter controls overlap with the timescale of the dynamics. So I took this figure from the UNIFI website, and I think it did a terrific job in explaining this change in the paradigm. Although many of the audience may be already familiar with the grid-forming and grid-flowing inverters, I want to quickly provide some primer on IBR dynamics for those who don't. At one end of the spectrum for IBR control, we have a grid-following controller, which is the mostly adopted technology in the current grid. The concept of grid flooring is that there is a steady AC voltage waveform that can be measured, and one wants to inject certain power into the grid by forming a current source. The name grid following means they follow or synchronize with the grid voltage waveform. The key part in doing so is through a feedstock loop. It wants to establish an internal representation of the terminal AC voltage waveform, and this internal filter version of the signal can be used for internal control loops. However, grid-following inverters have some drawbacks, such as lack of black star's capability and poorly damped oscillations or even instability in weak networks. This is because when the network is weak, the voltage signal is not clean for the PLL to check, and when the inverter inject current, the grid voltage waveform is more susceptible to such disturbances from the varying output of the inverter. There is stronger coupling between the two, which may cause bad dynamic behaviors. On the other end of the spectrum, we have grid-forming inverters, which achieves or forms certain desired voltage at its terminal. The synchronization to the grid in this specific implementation is through droop, frequency droop characteristic. The grid-forming inverter should be able to achieve black start and provide a range of grid services. Now, in between these two ends of the spectrum, there are numerous possible implementations. And I only showed some possibility here. So in the future, we need to make sure all these possible different controllers interact with each other properly, and we need a systematic tool to study this problem. So in fact, in one of our recent work, we proposed a UNIFI inverter control scheme that incorporates both a PLL and a droop frequency droop control. As such, it inherits the characteristic of both grid-forming and grid-following inverter controls. It regulates the voltage magnitude and active power at the same time. So in this sense, this UNIFI inverter behaves like a conventional generator. We use this UNIFI controller as a tool to understand the interactions of grid-forming and grid-following and their impacts on the grid dynamics at different locations in a systematic way, because now through the tuning of a single parameter of the droop constant in this unified control, the controller can be tuned to fall either towards a grid-forming or grid-following. We did a variety of case studies using several benchmark power systems, and the control scheme appears to be very robust. We also discussed in these two papers the black star process for this PLL-based control, as well as a mechanism for low voltage rest-rule, and most importantly, it can achieve autonomous transition between grid-connected and islanded operation of microgrids. So this demonstrates this autonomous forming of the microgrid when it is separated from the main grid through the droop characteristic, and the reconnection to the main grid when the fault is cleared through the PLL loop. Another thing I want to mention, which has been reported multiple times in the past, is that the dynamic performance of IBR-based resources depend fundamentally upon the strength of the network to which they are connected. This figure shows clearly that as the network becomes weaker, the step response of this unified controller becomes progressively more overdamped. And this red figure shows that the influence of the active power droop parameter on the inverter step response. And we can see that in the weaker grid, the grid following controller is more prone to oscillation and instability. And when we connect both type of inverters to the same bus, we can see that in a stronger grid, they behave similarly to each other, but in weaker grid, they display very disparate behavior, with the following one demonstrating more oscillation. Okay, so I hope the previous discussion made a case for the challenges in future IBR-dominated grids and the pressing needs in establishing new theory and tools to address these challenges. Our first research effort is focused on the stability problem. To ensure IBR properly interact with each other, we developed a decentralized approach to provide robust, scalable, and adaptive criteria in the case when the system is hosting a mix of grid-forming IBRs and synchronous machines. Our main argument is that the best way to address the challenge of achieving robustness and scalability is to get the local design right. I'll explain what this means for the rest of the talk. There are many key considerations when developing stability guarantee for inverter-based power systems. Firstly, the increasing adoption of small-scale IBRs will lead to a system of much higher order. This transition in grid structure necessitated scalable methods to enable detailed modeling of numerous IBRs. And second, renewable source IBRs, if not paired with battery, will lead to significant fluctuations in operating conditions in higher dimension, in faster timescale, and in larger in magnitude compared to conventional generation. So the approach should be robust to this operating point variation. And third, the conventional generation integration process takes repetitive tuning, and which seems to be obsolete in handling the faster adoption of IBRs in the future. Furthermore, there may be the case when adaptive plug and play happens in real time in future grids. The most suitable stability criteria should be able to adapt to such plug and play conditions. And last but not least, a barrier in IBR world is the lack of transparency in control implementation. This creates the famous chicken and egg problem. On one hand, the IBR manufacturer do not have or care grid model and cannot ensure their device won't deteriorate the grid stability. On the other hand, the grid operator does not have access to accurate IBR models due to proprietary information. This altogether motivates us to pursue a decentralized approach that only needs local information to be checked by individual devices, but to ensure system-level stability. In this project, we consider first a mix of Joule-controlled grid-forming inverters and synchronous machines. Consider a connected network-reduced power system with buses indexed by 1 to n, and without loss of generality, assume the first n inf are grid-forming IBRs and the rest are synchronous machines. The power system is modeled as this feedback interconnection as shown in the block diagram here. The forward path consists bus dynamic matrix H. And for the bus dynamics, the grid-forming inverters is modeled as multi-input, multi-output transfer functions, while the conventional synchronous machine is modeled as a single-input, single-output transfer functions for its second-order angle dynamics. So for inverter, it has both angle dynamics and voltage dynamics. The network is modeled as this linearized decoupled power flow without loss, and it sits at the feedback path. For the ICE bus, the exogenous signal P0 and Q0 are the change in power injection set points. The DP and DQ signals are the power fluctuations around the set points due to, for example, local loads. And the output signal theta dot and V dot represent the derivation of time derivatives of bus angle and voltage magnitudes. The P and Q are the power demand, and through the network, the signals theta and V are mapped to this power demand P and Q. We concentrate on the Joule-controlled grid-forming inverter as the start. The dynamics are composed of the Joule laws as described here, where MP and MQ are the Joule gains. The omega 0 and V0 are the frequency and voltage set points. The P0, Q0 are the power set points. FP and FQ represent the low-pass filters applied to the power measurements with time constant tau P and tau Q. The bus dynamic model for IBRs is then given by these two transfer functions for the P theta and QV coupling, and it contributes to a 2x2 matrix on the diagonal of this H matrix. The synchronous machine is modeled as a classic second-order angle dynamic equation, and its bus dynamic is given by this transfer function. So the bus dynamic H collects all the device dynamics on its diagonal with IBRs 2 by 2, and synchronous machine is 1 by 1 block. When model the power network, we make the following assumptions. First, the transmission lines are lossless. Second, at equilibrium, the angle difference across all transmission line is small. And third, the transient voltage magnitude lie in the range Vmin and Vmax. These assumptions generally hold true for most transmission systems, and we then consider a decoupled power flow, meaning ignoring the coupling between PV and Q theta. The corresponding terms in the network Jacobian is 0. This decoupling recognizes that in steady state, the active power are strongly coupled with voltage angles and reactive power with voltage magnitudes. In contrast, there is a weak coupling between active power and voltage magnitude and between the active power and the voltage angles. This is consistent with the first assumptions we made, which are physically justifiable for many practical transmission systems. However, they may not be appropriate for low voltage distribution systems where resistance are often high. The system model is abstracted into this figure. Nothing is changed from the previous interconnection, just simpler notations. For such system, one of the standard approach to establish decentralized stability is through passivity analysis. In a nutshell, the feedback interconnection of two passive systems is passive, and the feedback interconnection of a passive and strictly passive system is stable. So in this case, when the bus dynamic is strictly passive, the interconnection is stable for if the network model, the network Jacobian satisfies this condition, meaning it's a symmetric and it's bounded between 0 and 1. However, passivity condition may be conservative in some cases. And in one of the previous work by our collaborators, we exploited a limited network information to relax the passivity condition for the case with a single input, single output bus dynamics. The result established that if the bus dynamic is stable, we need to find a positive real function H. We refer to it as a multiplier function. And then if this condition can be satisfied, if there exists this number gamma between 0 and 1 such that this condition is satisfied, then the interconnection is stable as long as the network satisfies these criteria, this condition. To visualize this result, it is asking that the Nyquist plot of this system transfer function lie in a half plane that pass through -1 with angle defined by this multiplier function H. This relaxed passivity because it's no longer asking the plot to be living in the right half plane, but instead it is shifted to a plane defined by this H, and it's shifted towards -1. We have built upon this theorem and extended it to the case with multi-input, multi-output bus dynamics, and also extend the network Jacobian to include both angle dynamics and the P theta coupling and the Q and V coupling. This enables the modeling of voltage dynamics and IBRs. It is worth mentioning that this condition here for the network is easily satisfied, or more or less easily satisfied, if the Jacobian only has P theta coupling, say only consider the swing equation. But once we include the QV coupling, it is actually very challenging to make the network Jacobian satisfy this bound. There are two main things we need to attend to. The first one is symmetry, and the second one is to making the equivalent network matrix bounded between 0 and 1. To address this challenge, we progressively conduct loop transformations as listed here. So this is the trick. And the details, I'll skip you the detail in the talk, but they are provided in the paper that will appear in the general meeting this year. The key point while doing this loop transformation is in maintaining equivalence no matter what transformation you perform. And we show in the paper that this original network and the transformer network is equivalent to each other. Now, upon combining these two feedback branches, we obtain the corresponding forward path dynamics matrix G as given here, and the feedback network model L as given by this expression. So facilitated by this loop transformation, we are able to prove if the droop constant of the grid-forming IBR, this beta times m, satisfy this condition, then the network Jacobian L belongs to this set. Now the final theorem is summarized here. We establish a condition for the individual device that relies only on local information and that can be checked individually. This is for each of the bus. If we look at this bond, we can see that the first term is the difference of the voltage for the neighboring node, for the neighboring buses and the bus I. And this has a relatively clearer meaning that's the voltage difference across this transmission line. The term on the right-hand side is interesting because it is the self-susceptance of bus I, which is a summation of all the susceptance of connected lines. Recall that this is a reduced network, meaning the neighboring buses are all connected with IBRs or synchronous machines. One interpretation of this term is that if there are very long electrical distance between the two sources, that is when the BI is larger, then this beta times m needs to be smaller. What does this mean? Recall the QV droop relationships. This means that with the same amount of reactive power difference, the voltage is stiffer. Or in other words, the voltage control of the IBR is stronger. No, so conversely, if with longer electrical distance, but weaker voltage control, then the system is prone to instability. On a side note, we also think this variable, this term BI may serve as an indicator of the grid strength. And if so, higher VI makes the condition more restrictive, which corresponds to the observation that grid-forming inverter is more vulnerable to stronger grid. But that opens the whole new discussion of what is grid strength in future IBR-dominated power system. So better leave it for another day. So we illustrated the results firstly using a single inverter infinite bus example. The nominal parameter values of the system are given in the table. We choose various operating points and droop gain MQ as listed here. Then use eigenvalue analysis to study the small disturbance stability around the equilibrium point under these values. We can see that meeting the condition results in eigenvalues being having negative real parts in all cases, demonstrate the sufficiency of the condition. But when we choose a droop gain of 0.8, which is higher than this bound point established, that is 0.75, then the system is unstable. Similar results are demonstrated in the 3-bus system, and eigenvalues of the linearized system are presented in this table. Note that the meeting the condition result in stable systems in all cases, across all the chosen operating points, and the condition is indeed a sufficient condition. There are some existing works in the literature that all aim to develop this decentralized stability criteria, and each comes with the pros and cons. We aim to compare with those results in the future, but I want to highlight that the key strengths of our framework includes its capability to handle cases when the components are added or removed from the network, or when the operating point is changed. And it is truly a condition that only needs local information to be tested for individual devices. Furthermore, this framework enables us to do control synthesis based only on local models with a priori stability guarantees that hold independently of operating points and network configuration. For future work, we plan to incorporate grid-following, unified inverters, and other grid edge devices. As a first attempt, the chosen grid-forming inverter model is relatively simplified because we intend to capture the important system-level dynamics. Moving forward, we anticipate dynamic coupling between voltage and angle in the bus, leading to truly multi-input, multi-output coupling and a non-diagonal matrix H. We also plan to incorporate detailed modeling such as the lower level control loops and the transmission line dynamics in the future. We also want to relax the assumptions on lossless transmission line and the decoupled power flow formulation. And most importantly, we hope to connect with system operators and test and implement our results on larger power systems. So I think I'm running out of time, and before I close the talk, I want to mentioning that the previous decentralized stability guarantee is based on the small signal stabilities, and it considers the linearization of the network model and the stylized IBR model. I want to highlight that with the high variation of operating point and events in future power systems, it is important to consider large disturbance nonlinear phenomena, including both static problem and dynamic problem. We have made some initial study and observations, but probably I won't be able to cover those today. If you're interested, you can check my website where I regularly update the most recent works. I want to acknowledge my students, Zudika and Seshobon, for working on this very exciting problem, and my colleague and collaborator Enrique, and my former PhD advisor Ian Hiskin at the University of Michigan. So with that, I want to conclude the talk and open the floor for questions. Thanks.
Thank you very much, Sijia.
Yeah.